forget miles per hour. Seriously. The world we're about to dive into operates on a totally different scale. We're talking about a race measured in microseconds. That's millions of a second. This is the wild world of ultra-low latency, where fortunes are made and lost in literally less time than it takes to blink. Let's get into the race to zero. So, let's start with this number, 65.8%. What on earth is that? Well, in the high-stakes game of high-frequency trading, it's everything. It's the average speed advantage you can squeeze out just by using the right system architecture. And let me tell you, this isn't just a tiny leg up. This is the difference between spotting a market opportunity and getting there a split second too late. It is profit versus loss, all decided in an instant. So, why this crazy obsession with microseconds? That brings us to our first big topic, the microsecond battleground. We're going to look at these environments where these tiny, tiny slices of time mean absolutely everything. This quote right here just nails it. It's not just about being fast when things are going right. It's about being able to react instantly when things go wrong. Imagine a trading algorithm placing thousands of orders a second. A single millisecond of delay, or just one little error that isn't caught immediately, could spiral into millions of dollars in losses before a human can even process what's happening. And look, this race to zero latency, it's not just a Wall Street thing. It is happening all over the place. Think about an autonomous car that needs to slam on the brakes right now, or an AI that's giving you a seamless, real-time translation in your ear. From augmented reality that feels real to a surgeon performing a remote operation, none of these technologies can even exist without near-instant processing. The stakes are just as high, if not higher. So the big question is, how do you actually build systems that react this fast? I mean, it's not as simple as just buying a faster computer chip. It really demands a fundamental shift in how we even think about designing software. And that brings us to our next section, how to design for these instant reactions. The answer, it turns out, is a brilliant design pattern called Event-Driven Architecture, or EDA, and the analogy for it is perfect. Think of a traditional system like an old-school newspaper. It has to wait, gather all the day's info, print it, and then deliver it hours later. It's slow by design. Well, an EDA is like a live news feed on your phone. The second an event happens, bam, it's broadcast instantly to anyone and everyone who's subscribed. There's no waiting around, just immediate real-time communication. And this slide shows you exactly how that works. See, over on the left, you've got an event producer. This could be a stock market feed, a sensor in a car, whatever. It creates an event. That event goes straight to a central event broker, which acts like a super-fast digital post office. The broker then instantly delivers that event to all the event consumers on the right, and they can all act on it at the exact same time. The real magic here is that they're all completely decoupled from each other, which is what makes the whole system so incredibly fast and scalable. And the data? Oh, it totally backs us up. A study looking at high-frequency trading systems found that a traditional old-school system took over 15 milliseconds to handle an error. The event-driven system, just a little over 5 milliseconds. That's a massive 2/3 drop in delay. In the world we're talking about, that is an absolute game changer. But here's the thing. A fast software architecture is only half the story. To really push the limits of speed, you need that software to run on hardware that's just as quick and flexible. So now we have to go deeper down the stack, all the way down to the silicon itself. And this brings up a super important question. If you're really trying to shave off every last microsecond, can a normal general-purpose processor actually keep up? The short answer is no. You need hardware that can be perfectly sculpted for one specific task, getting you as close to the physical limits of speed as humanly possible. And that's where this amazing piece of tech comes in, the Field Programmable Gate Array, or FPGA. So think of it like this. A normal CPU is like a professional kitchen. It's really good at a lot of different things, but it's not absolutely perfect for any one thing. An FPGA, on the other hand, is like a kitchen made of Legos. You can literally rewire it and rebuild it, even after it's been made, to create the perfect custom appliance for one very specific recipe. And for that one task, it is unbelievably fast and efficient. This table really puts it all into perspective. Your CPU is your jack of all trades. Your GPU is a beast for doing tons of things at once, like for graphics. But now, look at the FPGA column. The two words to focus on here are ultra-low and deterministic latency. Now, deterministic is a fancy word that means it's not just fast, it's predictably fast. The task takes the same tiny amount of time every single time. For stuff where a random stutter could be a disaster, that kind of reliability is everything. Okay, let's zoom in on AI for a second, because this is where the different roles get crystal clear. A GPU, with all that parallel processing power, is the undisputed king of training a big AI model. That involves churning through massive amounts of data. But an FPGA, with its ability to be rewired and customized, it is the champion of inference. That's the moment you need your trained model to make one single, ultra-fast decision out in the real world. All right, so we have a lightning-fast architecture. It's running on custom-built hardware. What's the final piece of the puzzle? Well, it's managing the whole thing. How do you reliably build, deploy, and maintain these incredibly high-performance systems when they're live? This is where the discipline of MLOps enters the picture. Because this is where the rubber meets the road, right? It's one thing to have a fast model in a nice, clean lab environment. But how do you make sure it stays that fast when it's dealing with the messy, unpredictable traffic of the real world? How do you guarantee that response in under 100 milliseconds every single time? That takes a whole new level of operational skill. And this is exactly why a specialized field called low-latency MLOps has emerged. It takes all the standard ideas of automation and monitoring, but it looks at them through a new lens where speed is the only thing that matters. Every single step in the process, from handling the data to deploying the model, is just ruthlessly optimized to shave off any and every microsecond to meet that super strict time budget. So how do they actually make the AI model itself faster without losing all its accuracy? Well, teams use a few really clever tricks. First, there's pruning, which is basically like trimming a bonsai tree. You carefully snip away the less important bits of the model to make it smaller and quicker. Second is quantization, where you simplify the math the model is doing, kind of like rounding numbers to make calculations faster. And third, there's this cool idea called distillation, where a big, smart teacher model trains a smaller, faster student model to get almost the same results, but way more efficiently. They're all about that crucial trade-off between speed and size. But even a fast model isn't enough. The entire system built around it has to be completely obsessed with speed. Your data pipelines can't wait around for big batches. They have to be real-time streams. Your monitoring can't just look at average speed. You have to obsessively hunt down the slowest 1% of requests, what they call tail latency, because those are the ones that ruin a user's experience. And your whole infrastructure has to autoscale in an instant, ready for a huge traffic spike at any moment. Okay, so let's put all the pieces together. What happens when you combine this revolutionary software, this incredibly adaptable hardware, and these hyper-disciplined operations? Well, you unlock a completely new era of speed. So here's the crucial takeaway. Achieving this kind of speed isn't about finding one single magic bullet. It's about building a complete stack. You need the responsive, asynchronous design of an event-driven architecture. You need the custom-tailored raw performance of FPGAs. And you need the disciplined, speed-obsessed practices of low-latency MLOps. And when all three layers of this stack are working together in perfect harmony, the result is, well, it's pretty mind-blowing. We're not talking about milliseconds anymore. We are talking about systems that can operate with latencies in the single-digit microseconds, reacting in millionths of a second. And this leaves us with one final thought to chew on. We've seen how finance, robotics, and AI have all been transformed by this relentless race to zero. So, as our world gets more and more connected, more automated, what's the next great challenge? What's the next breakthrough that's going to be won or lost in the space of a single microsecond?